This is going to seem dumb, but then hopefully less so. What are the states of matter? Solid, liquid, gas. What's the definition of a solid? Yeah. The solid is with a defined or definite and you may not have really thought about that before in terms of defining what a solid is. You could probably all give me lots of examples of solids. I would hope you could give me examples of solids. But to think about like what actually makes something a solid, what makes a solid different from a liquid. So let's use this definition as our starting point. That solid is matter that has a definite shape and a definite volume, which means a certain amount of matter that is a solid will always take up the same amount of space, and it will always have a defined shape. That shape won't change based on its circumstances. So how is that different from a liquid? What does a liquid do with its shape and volume that a solid does not?
It has a definite volume, but not a definite shape.
Yeah, what does that mean that it has a definite volume? What does it mean to not have a definite shape?
Like it takes the shape of whatever you put it in.
Right. Has that been your experience with liquids? Hopefully. Yeah, they have a definite volume. You can have like a liter of water or a cup of water or a milliliter of water. But the shape of that is going to be different. If you pour it on the floor, it's going to spread out into a big puddle. If you put it in a long tube, it's going to be long and skinny. You know what I'm saying here? So the way that we would say that is that a liquid is matter with a definite volume and indefinite or undefined shape. Or another nice way to say that is that it takes the shape of its container. So you pour liquid in a particular container, it's going to take the shape of that container. But where do you think then that we go with gas? Based on this way of defining them, how would we define a gas? Yeah, gas would be volume with or matter with no definite shape and no definite volume. And that means that not only does it take the shape of its container, it takes the volume of its container. If I have a 600 milliliter beaker, how much air is in this beaker? Well, I guess the mass of air can be changing depending on things like the air pressure. But this is always going to be, the volume will be always 600 milliliters. So if this is exact, it's not exact, but let's say this is 600 milliliters volume, there is 600 milliliters of air in here. If we have a carbon dioxide tube or something and we evacuate all the air out by blowing carbon dioxide in, well, now we have 600 milliliters of carbon dioxide. So the air, even if there could be different masses of air, will still take up that volume. Another example is, let's say we were able to pressurize this. We could force more air into here, but it would still take up the same volume because it's still the same size container. So we could put more matter in there, but because it's a gas, it would still take up the same volume. When we get into the chapter of gases, we'll talk a little bit about why that is, and why gases are special like that. So we'll define gases as matter with indefinite volume, indefinite shape, or matter that takes the shape and volume of its container. Make sure that's still working. So that's our states of matter properly defined. And we're going to look at some of this stuff in lab on Wednesday, looking at some different states of matter, talking about how we can change states of matter. And so as we're thinking about changes of matter, and this we'll get into this more in the next part with the energy too, we have to look at two different kinds of changes: physical We talked about this in the last part when we looked at compounds versus mixtures, that kind of thing. What does this mean? What's the difference between a physical and a chemical change? And how would we determine that? How can you tell whether a change has been primarily physical or primarily chemical? Or let's just start. Can somebody give me an example that would fall into one or the other category? Either one. Yeah.
Like physical would be like taking like coarse salt and grinding it out.
Okay. We'll say grinding salt. Yeah, that's a physical change. What else? Crushing ice.
Metal to rust.
What was that?
Metal to rust.
Metal to rust for chemical change, yeah. When metal rusts, that's a chemical change. It's actually the iron that's rusting. Yeah.
Would melting ice be physical?
Yeah, melting ice would be a physical change. Let's try to get a few more in here, and then we'll put them into some kind of larger definitions.
For chemical, like burning something.
Yeah. Anything in particular? What's your favorite thing to burn?
Firewood.
Firewood? Okay. Is that what the kids are calling it these days? Any others? Nobody's got any more? What? You had one? Okay, spoiling milk. Where would that fit? Yeah, I think that would be chemical. Although there's some different things going on there. We'll talk about that one. All right. So what, if we could, here's a few of them. If we could summarize what's happening on one side versus what's happening on the other side. Anybody want to give it a shot? If you look at these examples, what is it that makes some of them go on chemical changes, and what is it that makes the other ones go on the physical side? Yeah.
Physical is something, somebody's physically doing something to it. It's the second party involved, and then chemical is just leaving alone in its natural state over time.
So, like when it snows in the winter, and then it naturally melts, right?
Yeah.
But that's still in the physical change.
Chemical is irreversible.
So some of the chemical chains are irreversible? Okay. That's true that our examples are mostly irreversible. Although that's not true in general of all of them, but I could see that.
Physical is like state and size and appearance, like it like remains the same even though like it's broken down.
Yeah, that's kind of the main thing here, the main difference. you'll notice that in physical changes, we don't actually change the identity of whatever it is we're doing something to or that's being done naturally. So for a physical change, we could change the size, shape, appearance, kind of these things. So it could change the appearance. It could look quite different. Water looks quite different from ice. However, we don't change its identity. We don't really change what it is. When ice melts, it's still water. It's still made up of water molecules. We haven't essentially changed what that is. In the chemical changes, a key thing is that we form new substances. In the metal example, we take iron and we turn it into iron oxide. Iron is, of course, shiny, metal-looking. You can bend it. And rust is kind of brownish and brittle and falls apart and is a totally different thing. Burning firewood, we take wood, which is carbon, hydrogen, and oxygen in these big cellulose components, and we break it down into, what are the products of burning, you know? Anybody know?
Ashes.
Ashes are left over. Yep, so ashes are when the carbon in there has condensed more, so there's more carbon in the ash, and that's why it's black. But actually there are two major products of burning or combustion that are carbon dioxide and water vapor. And in fact, if you had perfectly efficient combustion, meaning you had all the oxygen needed for the combustion, there would be no ash left. There would be no soot at all. It would all have turned into carbon dioxide and water vapor. So that's, again, forming new substances. And then spoiling milk, I think that also fits, because the spoiling characteristics, the gross taste and smell and everything, are new substances, new molecules that are being formed by the bacteria. So I think that's the main thing, is the main question is, are you forming anything new, or are you keeping the same thing, just putting it in a different form? We might also use those terms if we go back up to our mixtures and substances. Mixtures can be separated by physical means, but compounds can only be separated by chemical means. So when we take our raisin pancakes and we pull all the raisins out, and then we just have pancakes and raisins, we haven't really altered the substances of anything, but we've changed the mixture. It's no longer a heterogeneous mixture. It's now two homogeneous mixtures, a mixture of pancakes and a mixture of raisins. So that might be another way to think of those. You can think of those. All right. Let's talk a little bit about energy and temperature. What is energy? I mean, it's a word you've all heard, right? What does it mean for the ability to do work?
The energy is put in.
Yeah, so energy is a quantity that we can assign to a given person or a molecule or whatever, and then it's its capacity to do work, which means to act on something else, which means to transfer its energy to something else in a particular way. So energy we would define as the capacity or ability to do work. And if you take physics, you'll learn about work and all of that. Anybody excited to take physics? No? Might be fun. Sign up for it next semester. Why not? Be a good time. Everybody's just staring at me like, that would not be a good time. Don't even suggest that. It's not even fun. But we're going to focus mostly on part of this that has to do with heat. Anybody know what heat is?
a lot of energy.
When there's a lot of energy, we might have heat. Actually, there can be heat with a really small amount of energy as well. Heat is really, as we define it, heat is a transfer of energy. So there are two ways to transfer energy from one thing to another. One is through work. So like you pick something up off the floor, you've transferred your energy to this thing that is now up here. Now it has its energy, so if you let go, it can fall back down to the floor. That's one way. That's called transferring energy via work. Another way you transfer energy is through heat. You can hold something that is cold, and some of the energy from your body will go into the cold object to make it warmer. Now it has more energy. Then if you let go, it can dissipate its energy to the surroundings through heat. So two ways to transmit energy. Heat is one of them. And how do we measure heat usually? A thermometer. Yeah, a thermometer. So let's look at temperature, which is a way to measure energy. And what are the main units for temperature that we're concerned with?
Fahrenheit and Kelvin.
Yeah, degrees Celsius, degrees Fahrenheit, and kelvins. Notice Kelvin doesn't have a little degree sign next to it. It's actually not degrees Kelvin. Kelvin is a unit like gram. So you would say 250 kelvins. Although we don't always say it that way because we're used to the other scales. But technically it is a unit. You can have millikelvins or kilokelvins, whatever. Has everybody used all these scales before? Yeah. Where might you use degrees Celsius? What?
Remind me, it's been a while.
Well,
Europe.
Europe. Pretty much everywhere else, actually. Right? But also lab last week, right? We measured the water and stuff in the air in Celsius. So yeah, most of the world uses degrees Celsius. We in science often use it also. It's a nice even scale. What are some things you know about the Celsius scale? Anybody know anything about it?
0 is freezing.
0 is freezing of
Water.
water. And anybody know what's the boiling point of water in Celsius? 100. So it makes a nice even scale that you've got 0 to 100 for water. What's body temperature in Celsius? Yeah. 37. Yeah, that's another good one to know. And then degrees Fahrenheit, where would we use that? Of course, like weather reports and that kind of stuff, right? That's kind of our day-to-day experience around here. And what about Kelvin? Where do we use Kelvin? Why? What? Absolute 0? What about it? Yeah. Temperature, as we'll learn a little bit more in the gas chapter, temperature correlates to molecular motion, like how molecules and atoms move. They're always moving. No matter whether they're in a solid or a liquid or whatever, atoms are always having some motion, and that correlates to temperature. So if you could cool things down to the lowest possible temperature, that would be when atomic motion stops, and that's called absolute 0. Yeah.
We've never gotten a 0 Kelvin, have we?
No.
And how do we know what it's equal to?
Well, we define it. So 0 Kelvin is when molecular motion stops.
Okay.
So we can measure absolute 0 in places like space where there's no motion. There is no molecular motion. And also we've gotten within tiny, tiny fractions of that. So you can kind of say that it's up to this limit. Like if you keep cooling things down and you keep sort of approaching this one number, you can assume that that's where you're going to end up. So we've gotten within, I think, like 0.00000, I think like 10 or so zeros, 1 degrees. So like really, really close. But that's the use of Kelvin, is that this 0 point is actually 0. There are no negative degrees in Kelvin. It just goes to 0. So if you're dealing with really cold stuff, Kelvin's good. Also, a lot of the calculations that we do in chemistry with regard to energy require that there be 0 at the bottom, at the base of your temperature. So we have to convert all our units to Kelvin so that we can actually do those calculations. The other scales don't work because their zeros are not actually 0. They're just kind of in the middle, and they have more to do with water. So I want to put this chart up from the book so we can think a little bit about what these scales are. All right, everybody kind of see that? Here are 3 thermometers that are the same size, but whose units are in 3 different things, and they're all in boiling water. So you'll see that the point at which that water is boiling for Kelvin is 373, for Celsius is 100 degrees, and for Fahrenheit is 212 degrees. Then you've got normal body temperature here, 98.6 Fahrenheit, 37 Celsius, 310 Kelvin, and then you've got the freezing point of water down here. A couple things to note here. A Celsius degree is the same size as a Kelvin. So there is the same distance between boiling and freezing, 100 kelvins, as there are in Celsius degrees. But Fahrenheit degrees are smaller. There's more degrees between those 2 points in Fahrenheit than there are in Celsius. And that makes converting among the scales a little bit trickier. We're actually not going to do that. Well, I'm gonna show you those equations, but I don't think that that's in the whatever the objectives that you actually need to remember these equations. But for your information, we could use these. We could certainly use these in some of the homework. The easiest is to go from Celsius to Kelvin. So you can take your temperature in Celsius, and you can add 273, and you've got your temperature in Kelvin. Because Kelvin degrees are the same size as Celsius degrees, it's just that it's offset. It's like starting from here instead of starting from here. They're the same type of scale. So all you need to do is add or subtract 273 to go between Kelvin and Celsius. Same thing with this one. The temperature in Celsius is going to be your temperature in Kelvin minus 273. Where it gets tricky is going between Celsius and Fahrenheit. Because not only are your scales offset now, but also the degrees are different sizes. So you have to do a conversion type thing like we did before to correct for the size of the degree, but then you also have to do this offset thing to correct for the scale. So the equations look like this. To convert from Celsius to Fahrenheit, you take your Celsius degrees and you multiply it by 1.8 because Fahrenheit degrees are a little smaller, so there's more of them in that same range. And then you add 32 to offset that range. To do it the other way, you have to first subtract the 32 and then divide by 1.8. So you have to take your Fahrenheit degrees, subtract 32 for that 32 degree offset, and then divide by 1.8. That's how you get from one to the other. Again, check the objectives on Blackboard, but I don't think you need to know these equations. I think those will be given to you. If I'm wrong, we'll go back over it next time. All right. So now we've got temperature. You feel good about measuring temperature? Was that okay last week? Like using thermometers and stuff? If you didn't get a chance to finish your lab report, just a couple questions. I don't think everybody turned it in last week. So if you still have that, if you got it tonight, you can turn it in, or on Wednesday. Generally, our labs will be due the next week. So if we do a lab on Wednesday, the report would be due the following week. So this Wednesday would technically be when last week's lab was due. But I know a lot of people just finished it that night and turned it in. So anyway, let's talk about energy and how we measure energy. So temperature doesn't actually measure energy. Temperature measures temperature. Remember that heat is a transfer of energy. And so in order to measure energy or heat, we really need to measure for a change in temperature. So if something changes temperature from here to here, that's evidence that there has been heat transferred or energy transferred. Let me show you how that works. A couple terms you may have heard. Exothermic and endothermic. Have you heard these terms before? Anybody? Has anybody heard these terms before? I don't know if they're things that you know. But they were applied to, in a particular system or a particular process, what's happening. An exothermic reaction is one that releases energy. Technically, the definition is it transfers energy from a system to the surroundings. But we can think about that as releases energy. For instance, if you do a chemical reaction and it's exothermic, it's releasing energy to the outside. So what's going to be your experience of that chemical reaction?
The temperature will rise.
The temperature will rise or it'll feel hot. So if you do a chemical reaction and it creates heat, we can call that an exothermic reaction. Like burning. It's kind of like the classic example. You burn something, it gives off this heat, and that's an example of an exothermic process. The opposite is an endothermic process. We're less familiar with these. Endothermic processes absorb energy. How would you experience an endothermic reaction? A chemical reaction. If it absorbs energy instead of releases energy, what's that going to seem like? How are you going to experience that? Well, yeah, except what about in like a chemical context? So we pour some stuff together and it's an endothermic reaction. What's that going to be like? What? I think everybody's kind of thinking it, but not really sure. It's actually just the opposite. So that's going to feel cold. Like you said, being out in the cold. But an endothermic process is one that pulls the energy away from you. So if you do a reaction and you hold it in your hand and it feels cold, that's evidence it's an endothermic reaction. Because what's happening is energy is being transferred from your hand into the the reaction, and that makes you feel cold. It's pulling the energy from the surroundings. We don't experience that a lot. We are going to see some examples of this in lab, but if you've ever seen things like those instant cold packs, you know what I'm talking about? You can like put them in an emergency first aid kit or something, you kind of crack them open and then they get really, really cold. That's an example of an endothermic reaction. It's a chemical reaction that is pulling in energy from around it, and that's making the parts around it cold. And that's where you might experience that. So let's talk about some of these processes. But to do that, we have to get our units straight again. Units for energy, a little bit complicated, unfortunately. There are a lot of units that we use for energy because there are different kinds of energy and different scales, and people in this discipline like this unit and people over here like this other unit. So we're going to see a lot of different units, but luckily we are very good at converting from one unit to another now, right? So we're like, I don't know. So we can always go back and forth. What are some units of energy that you might have heard of? Does anybody feel like they may have heard of a unit of energy? Like something that energy is measured in?
Calories?
Calories, yeah. We're going to talk about calories. Abbreviation for that is just cal. What else? Joules, right. Big J. You know any other ones? Those are the big ones. There are a few more. Heard of a volt, like in a battery? That's a measure of energy, of electrical potential energy. And then another one that we see sometimes, especially when we talk about fuel, is a BTU. Have you ever heard of a BTU? It stands for a British thermal unit. It's used often to talk about how effective a fuel is or how efficient a fuel is. So if you look up like gasoline information or diesel, or like whether biodiesel is better than regular diesel, that kind of stuff, you'll see numbers in BTUs. You also might see it in things like furnaces and air conditioners. They're usually rated for a certain number of BTUs. It's the amount of energy they put out, the amount of heat they can deal with. The important ones that we're going to worry about are calories and joules. So here's some numbers. Again, you don't need to remember these, but 1 calorie is about 4.18 joules. So they both measure energy. I'm going to show you what we use calories for, which has kind of a very simple definition. And then we'll sometimes convert to joules because that's more of a standard measurement. And then this is where it might get a little bit confusing. The calories on our food, for instance, tonight I'm eating, according to this, 550 calories of M&Ms. That's probably not good. But have you ever seen that like on food it tells you the calories? But you'll notice those calories have a capital C, and these calories have a lowercase c. And that's actually really different, sadly, because the really confusing part of that is that C is one of the letters that the uppercase and the lowercase ones look the same. So if you just kind of draw it wrong, suddenly you're off by a bunch. So 1 calorie, big C calorie, the calories that we see on our food labels are actually kilocalories. That is 1,000 calories. 1,000 little c calories. So if you make your c too big or too little, when you write cal, you're off by 1,000. Actually, a factor of 1,000. So you've multiplied or divided your thing by 1,000. All right. So that's actually an important thing to keep straight. And so outside of the US, and even here for some of them, you'll notice that these will say kcal instead of just calories to try to avoid that confusion. Here you'll often see both of them. It'll say calories and then in parentheses kcal. Outside of the US, it'll just say kcal. Where does that calorie come from? It takes 1 calorie, little c calorie. See, I almost made my c too big. Screwed up the whole definition. To raise 1 gram of water, °C. Well, it looks like I'm probably not actually going to finish it, so not the full 550 calories. It takes 1 calorie to raise 1 gram of water, 1°C. That's how much energy has to be put in to 1 gram of water, which is 1 milliliter, right? Not much, to raise it 1°C. So by measuring the temperature change of water, we can determine how much heat is transferred from a particular process. This is called the specific heat of water. And it's written in kind of a confusing way. 1 calorie per gram degree C. That's kind of the fraction way to write what we just said. It takes 1 calorie per 1 gram, 1 degree C. And that's called the specific heat of water. The way that this can help us is by calculating how much a certain known amount of water changes temperature. So if we have 100 grams of water, and it goes from 25 degrees C to 65 degrees C, we can calculate how much energy was used based on this equation. So if 1 calorie means 1 gram of water goes up 1 degree C, how many calories is it for 100 grams of water to go from 25 to 65? Anybody see how we might be able to do that?
Would you do the reverse, what we, like how we did earlier for the milliliters per gallon thing?
Yeah, you can start, I think you're on the right track, yeah. That you can kind of take that quantity, that specific heat quantity, and multiply by grams to cancel grams, and multiply by degrees C to cancel degrees C, and then you're left with calories. And that's your amount of energy. So often we write it like this. The heat that was, which is the energy that was transferred, is the mass of water times the change in the temperature, which we sometimes write delta T. That Greek letter delta means change. So change in temperature times the specific heat of the substance. So in this case, that's 100 grams of water times the change of temperature, which is what here? How many degrees change should we have? 40, yeah. 65 minus 25 gives us a 40 degree change in temperature. And then times the specific heat of water, which is 1 calorie divided by gram degrees C. So grams cancel, degrees C cancels, and we end up with 4,000 calories. So 4,000 calories is how much energy it takes to heat 100 grams of water from 25 degrees C to 65 degrees C. Now, one thing we do, there's an experiment called calorimetry, where we burn something like food, and we use that energy to heat up some water. We measure the change in water, and then we know how much energy was in the food. And then that's how you can calculate something like the calories in food, is you can burn it in oxygen and measure the heat released by how much it can heat up some water. All right, a couple last things to talk about. Now that we know some things about heat, let's look at some heating curves. I'm going to pull this again from the book. When we look at changes of state, that is like going from solid to liquid to gas or something like that, here's a picture of that. So you've got solid ice, and then you can melt to water. You can do something called sublimation, actually, to go straight to the gas. And then that gas can condense back to the water. So there's this kind of cycle. Another way to look at this is how much energy does it take when we heat something up to melt and then vaporize it. And what that is, or what we get from that is what we call a heating curve. So let me see where that heating curve is. There we go. I'm going to pull this into our notes so we can annotate it a little bit. This is what we call a heating curve for water. And if you haven't seen a graph like this before, the y-axis up and down is temperature, and the x-axis is heat. And so heat is not, what this means is heat is not always correlated to a temperature change. Just because there's an increase in heat does not necessarily mean that the temperature is going to go up. So what we want to do is follow this curve along and see what's happening at each stage. So we're going to start way down here at minus 40 degrees C, where we have solid ice. As we put energy in, we are heating that ice up. The more energy we put in, the more it heats up until we get to 0. What happens at 0? It melts. The ice melts and becomes water. But notice what happens to the heat. We can actually have ice at 0 degrees that does not melt. So if you can hold ice at 0, you can have ice that exists at 0 degrees and is not melting because it requires more energy to melt that ice. You have to put in more energy. You have to put in about this much energy, which is called the heat of fusion or the heat of melting. And then you got liquid water, and you have liquid water at 0 degrees also. So at that 0 degree point, you have actually solid ice and liquid water. You can have liquid water at 0 degrees, you can have solid ice at 0 degrees. Depending on the energy, you can actually push it to one side or the other. But let's say we've got the water now, we've got 0 degree water. So we put in that heat, and we're heating up that water up to 100 degrees. And then what happens? What happens to water at 100? It boils. But look at this huge line here. What does it mean that there's this really long straight line and flat line at boiling, at the boiling point of water? Yeah, it takes a lot of energy to boil water, even after it's at 100 degrees. And you may have experiences if you've boiled water on the stove, where you get a pot and you put water in it, you put it on a stove and heat it way up. It gets hot pretty fast, right? Hot enough that you can't touch it pretty fast. But then it's still a while after that that it actually starts boiling. Because it actually takes way more energy to boil water that's at 100 degrees than it does to heat up water from 0 to 100. This is approximately to scale. Look at the difference in heat between 0 degree water and 100 degree water. It's not that much, right? And then it takes all of this more energy to actually boil it. So to break up those water molecules from one another takes a whole lot of energy. And then we finally have the gas. And we see the water vapor. So look at that picture of that water vapor. Water vapor is little water molecules that are flying around and not connected to each other. This is something that I always ask at some point, and I always see a lot of people saying wrong, that when water boils, it does not break up the hydrogen and oxygen bonds. Remember the chemical versus physical changes thing? Boiling water is a change of state. It's not a change of identity. If we broke the oxygen and hydrogen bonds, that would be a change of identity. That would be a whole new compound. So when we boil water, we separate the molecules from each other, but we don't change their identity. They still are molecules of H2O. Does that make sense? Because I'll often ask things like, when we get into this later, why does this thing have a higher boiling point than this thing? And people will say, oh, well, the bonds are stronger in the one with the higher boiling point. It takes more energy to break them apart. But that's not really true because the bonds aren't being broken apart when we boil something. The molecules are just being separated from each other. So please try to keep that in mind. If you think of these little pictures where you've got water molecules packed in ice, water molecules around in the liquid, and then water molecules on their own as gases, but still water molecules that whole time. So you kind of try to keep that straight. You can keep that sort of straight? Yeah. So let's look at how we might answer a question or a problem that deals with a heating curve and how we can interpret that. So I'm going to jump back to the book here. I'm going to pull this picture in instead of trying to draw it by myself. Here's a heating curve for chloroform, a solvent. And there's actually, I think there's another couple parts of this too. Yeah. All right, let's see if we can answer these questions based on that heating curve. So you'll notice it looks a lot the same as the water one, right? Kind of has the same shape, which makes sense because chloroform also has a melting point and a boiling point and kind of goes through the same process. So based on that heating curve, what would you say is the melting point of chloroform? At what temperature does it melt? Yeah, it looks like just below -60, so maybe -50. Yeah, it's going to be more than 60, right? More negative than 60. So it's going to be -63 or something, let's say, right? Okay. What's the approximate boiling point of chloroform? Yeah, like +60. It actually looks like it's a little below that to me. So 55 or something, 58. Yeah. Great. Identify the segments A, B, C, D, and E as solid, liquid, gas, melting, or boiling. So what would A be? Solid, yeah, during that. What about B? That's melting. C? Liquid, and then D? Boiling, and E is a gas. So you gotta follow it through its phase changes that way. And then let's look at these different temperatures and decide if chloroform is going to be solid, liquid, or gas at each of those temperatures. So at -80 C, what is it? It's a solid. How do you know? Yeah, once we've identified these phases, we can go over to the graph here and say, well, -80 is like here. So that's right there where we're saying it's still a solid. What about -40? Liquid, yeah, that's kind of here. 25, still a liquid. And 80, yeah, that's going to be good, I guess. There is an assumption here that we haven't, that they don't really specify. Anybody know what that is? What are we assuming about chloroform?
It can be in all three phases.
Yeah, that these are actually solid, liquid, and gas phases in the same way that like water is, which is true. But there are other things. You could have a heating curve for something that's changing different liquid phases, for instance, or different solid phases. Ice has various different phases depending on the pressure and the temperature. So we're kind of assuming that this is your standard solid, liquid, gas. But you know, that's probably a pretty good assumption, especially because that's what all the questions are being asked about. So I think we're probably okay with that. All right. What time is it? We're almost done. This has seemed like I talked a lot tonight. I'm sorry. Like we should have, there weren't a lot of problems to break it up in this one. There was a lot of talking. All right, this is our last thing. And then you should be all set to do all the homework for chapter 3. Let's look at how energy works in food. Now, we already talked about the issue with the calories conversions, but let's look at the calorie density in food and then figure out how we can calculate calories by knowing what types of other things, macronutrients, are in the food. we're going to look at, we're not going to confuse ourselves. We're going to use kcals instead of big C calories. And we're going to look at kcals per gram. That is, how many kilocalories are in each gram of a given substance. Now, in general, and there's always some variation here, but in general, these three categories of types of food molecules can be generalized to have these types of calorie properties. So fats, in general, will have about 9 kilocalories per each gram. So each gram of fat have about 9 kcals. Proteins will usually have about 4 kilocalories per gram. And carbohydrates will be generally 4 kilocalories per gram also. Now, of course, we know there's lots of variations within these categories, and how your body actually accesses that energy or uses that energy is very different. You can, talk to a nutritionist or study that yourself and know there's quite a lot to know about that. But just, you're taking these raw materials and measuring them, and this is generally what you're going to get out. So you can say, all right, we have, and you'll see some homework problems like this, we have a particular food that has 37 grams of carbohydrates, 19 grams of fat, and 23 grams of protein. And we can calculate what is the total energy in the food. You know how we would do that? How would you do that? If we know the calories per gram for each nutrient, how could we get the total calories for this particular food? Yeah, you'd multiply each one by its kilocalories per gram. In other words, we can think of this as another type of a conversion problem. We've got grams of stuff listed, so grams of carbohydrates, and then this tells us there are 4 kcals per each gram. So we could say 37 grams of carbohydrates times 4 kilocalories per gram. Grams cancel, and we're left with kilocalories, 150. And we can do that with each of these. So for the fats, that's 19 grams. Right, so more calories. Fat is more energy dense. There's more energy in it per gram.
Is there a reason why you're rounding them?
Just,
Okay.
yeah, just because.
Okay.
Technically, it's because we only have 2 digits on these measurements, so we have to
okay.
carry that over. But if you prefer to keep the numbers, that's fine. And then 23 grams of protein. It's going to be 92. So the total is we would add those all up and get 412. If you want to check that sometime, you can, and we'll do this in lab, but you can take your snacks. Oh, they didn't actually put the nutritional information on the bag. It's only on the box. That's why they need the box. Because it's all empty here. There would have been plenty of room. But you could look. You could do the same calculation on any nutrition label. Calculate your carbohydrates by 4, protein by 4, and then fat by 9, and you should come up with about the same number as what's been reported on the label. So I did not make it through all my 550 calories of M&Ms, so I'll have to save those. All right, we'll stop there. So you should be well served to work on the homework in chapter 3. A lot of these energy type problems. Mostly, it's going to be things dealing with unit conversions and these heating curves. We'll have lab on Wednesday, and there is a pre-lab, so make sure you complete the pre-lab activity before coming in on Wednesday, and just turn that in as you come in. Anything else? I don't know. Let me know if you have questions. Otherwise, I will see you Wednesday. Oh, and it's going to be hot all week, so make sure you wear appropriate lab clothes on Wednesday. Make sure you have closed-toed shoes and pants at least down to the knees.